Morning, sir.
We welcome everyone to the second talk of the day. The second talk is on the role of artificial intelligence, machine learning, in fighting a pandemic. We are privileged to have with us Dr. Vijayan Sugumaran to deliver this talk. This session will be chaired by Dr. S. Ravikumar. Dr. S. Ravikumar is Principal Scientist, Multidisciplinary Center for Biomedical Research and Assistant Director of Research, AVMC. He completed his PhD in biochemistry and molecular biology at Pondicherry Central University, India. He has worked for more than 9 years in South Korea as a postdoctoral fellow, as research professor and assistant professor of research. His research interests lie in the area of diagnostics, pharmacogenetics, genetic engineering, health informatics, and nanotechnology. He has published more than 50 research articles in index journals and has also received a patent. Sir, I request you to chair the session.
Thank you, Aarti. I'm audible?
Yes, sir.
So welcome, sir. Welcome, Dr. Vijayan Sugumaran. I'm very happy to be chairing the session for him. Dr. Vijayan Sugumaran is our recent collaborator for our Center for Biomedical Research. So welcome, sir. So Dr. Vijayan Sugumaran, sir, is a co-director of Center for Data Science and Big Data Analytics at Oakland University. He has received his PhD in Information Technology from George Mason University, US. His research interests are in the areas of big data management and analytics. Sir has published more than 275 reviewed articles in journals, conferences, and books. And he has edited nearly 20 books and serves as the editorial board of 8 journals. Sir has published in top-tier journals such as Information System Research, ACM Translation on Database System, Communication of ACM, IEEE, Big Data, IEEE on Big Data, Engineering Management, and so on. Dr. Sugumaran is an editor-in-chief of International Journal of Intelligent Information Technologies. He is a chair of the Intelligent Agent and Multi-Agent System mini-track for American Conference on Information Systems. Sir also is a distinguished professor of management of informatics system, and today Sir is going to give a talk on the role of AI in healthcare. Sir, the stage is yours, sir.
Thank you. I think you need to enable me to be able to share the screen.
I think you can share your slides right now.
Okay, all right, so let me try again. Okay, all right, very good. Okay, so can everybody see my screen?
Yes, sir, well, you can.
Okay, very good, very good. Okay, thank you, Ravi Kumar, for the one kind introduction. I greatly appreciate the opportunity to present at this conference. I have visited AVIT many times. I mean, obviously, I'm from Chennai, so every time I come to Chennai, one of the places that I stop by is AVIT, and I'm very happy to participate in this conference. So my presentation is going to be completely different from what Dr. Muthukumar's presentation is. So I'm coming from the computing angle, and so I want to kind of divide the time into 2 halves. The first half, a quick review of AI, machine learning, deep learning, just so that everybody is on the same page, and then we look at some of the applications of them. So even before I get to that, I just wanted to take a minute to kind of give a rough idea about where we are. So we are in Rochester, Michigan. So when I mention Oakland University, sometimes people think we are in California. So there's a big city in California called Oakland, California. And so sometimes people think that I am from California. So we are actually located in Michigan, very close to Detroit. So we are in a city called Rochester, which is suburbs of Detroit, about 45 miles north of Detroit. So just to give you an idea of where we are. Oops, sorry. So some images from Detroit. So the building on the right is the GM headquarters building, Renaissance Center. The building at the bottom right, my right, is the Chrysler headquarters building. The building at the bottom left is the Ford headquarters building. So obviously Detroit is the auto capital of the US. We used to call it auto capital of the world, but I don't think I can say that anymore. But at least, within the US, we are in the automotive country, obviously. And so the picture on the top left is actually the downtown Detroit. So this river that you see, this actually separates Canada. The other side of the river is Canada. So there's a Ambassador Bridge that connects Detroit to Windsor. And then there's also an underground tunnel. So this bridge alone is responsible for about $2 billion worth of trade between US and Canada. So that's a very, very important artery that connects Windsor and Detroit. Detroit is actually, pretty old city, lots of sports, music. And so we got all kinds of sports, baseball, American football, ice hockey, basketball, motorsports, and the likes. And so I thought it'll be nice to show you some pictures from in and around Detroit. Okay. So, so I just wanted to take a little bit of time kind of going over some of the terminology. So people use these terms interchangeably, but it might be worthwhile to spend a few minutes figuring out exactly what they are and how they fit with each other. So, people, mention AI, machine learning, and deep learning. So the field of AI has been around for a very long time, even though it has kind of gotten renewed interest now. But, if you think about AI, it started in the late 50s, early 60s, and AI was introduced with a very big fanfare. But then it fell out of favor for a while because, when AI was introduced, they said, it's going to solve the world's problems, and then it never really materialized. And so in the 80s, then there was a big push to kind of narrow down the scope a little bit. And so let's identify some specific tasks or specific things that we can do well using the technology, right? And so machine learning is sort of a subset of AI. And so machine learning focuses on very specific kinds of problems to solve. And we got a little bit better at that. And then now, starting from 2010 onwards, there's a big push towards what's called deep learning. And so I will kind of explain what they are in a little bit. Okay. So a quick review of machine learning. So if you think about computing, normal computing, what happens? So we write code in any high-level language, be it Pascal, Fortran, C, C++, what have you, Java, and then we provide a set of input, and then it generates an output, right? And so that's typically how traditional programming works. However, in machine learning, we sort of flip the table a little bit. So in machine learning, we provide the input and the output, and then we try to build a model, or we try to generate a program that can help us identify the relationships between the input and the output, so that when I provide new input, I want to be able to generate appropriate output, right? And so that's the main difference between traditional computing versus machine learning, deep learning, and AI kinds of paradigm. So it's a fundamental shift in how we think about building computing systems. Okay. So within machine learning itself, there are different kinds of models that we can have. So typically, people will talk about descriptive, predictive, and prescriptive machine learning models. So descriptive model is basically trying to kind of understand what happened given a set of data, right? And so typically we try to identify some basic relationships between, say, a set of variables, okay? In predictive modeling, we not only do descriptive, but then also build some models that we can use to be able to predict, given a new set of input data, what would be the output, the corresponding output, right? What will happen in the future, right? And so that's typically what's called predictive modeling. And then if you take it one step further, based on predictive modeling, given a particular context, we can also prescribe what to do, what kind of mitigative actions you can take, right? And so that's typically called prescriptive modeling, okay? So typically when people talk about machine learning, you could build kind of a descriptive model, you could build a predictive model, or you could build a prescriptive model. So when we build these machine learning models, typically we have a process that we go through. One of the common process models that gets used in the industry is called CRISP-DM, Cross-Industry Standard Process for Data Mining. So basically, this process model starts off with understanding a given business problem, for example, and then in order to solve the problem, what kind of data we need. And then once we have access to the data, we may need to understand the data. We may need to prepare the data. And so once we have the data to work with, then you can build a model. And then once you have the model, you can do testing and evaluation, and then you deploy the model, and then you put it into production, and then you monitor the model, and then you kind of go through an iterative process. So that's typically referred to as the CRISP-DM model. So any machine learning AI kind of development work would follow typically this kind of a process model. There is another model called SEMA, which is also very, very similar flavor. This particular model comes from the SAS Institute, Statistical Analysis Software Institute. So they are one of the big players in the analytics space. And so this also has pretty much a very similar flavor. You start to work with some representative data, and then you explore the data, visualize, understand the data, and then you may need to do a lot of modification of the data, for example. One of the things that you will commonly have to do is if you're getting a lot of dirty data, how do you deal with missing values? How do you aggregate some data, right, to cut down the number of variables that you have to deal with, right? And so there are a lot of preparatory kind of activities that would take place. Once we have the good quality data available, then you build the model, assess the model, and then put it into production and kind of repeat the process. So both CRISP-DM and SEMA are very, very similar process models. Under machine learning, there are 2 or 3 broad categories of models that we can build. So typically, you have one class of models called supervised learning models. So the basic philosophy in building supervised learning models is, teaching by example, right? And so we provide positive examples and negative examples, and then from this data set, we try to learn something useful and build a model. So that's typically what are called supervised learning models. Or in other words, I have some sort of a model in mind, general structure of the model, and then I will try to estimate the parameters of the model. So that's typically what's called supervised machine learning models. There are very standard supervised learning models that people use. Decision trees, gradient boosting models, neural networks, random forest, regression analysis. There are many, many variations of regression analysis, logistic regression, and things like that, and then support vector machines. And so these are all standard supervised learning models that are out there, right? So the thing to keep in mind is, so all of these models are estimating the parameters of a preconceived model, right? If you think of a linear regression model or a logistic regression model, you're just basically estimating the coefficients of the equations, either linear or nonlinear models, right? So that's typically what are kind of grouped as supervised learning models. The other class of models is typically called unsupervised learning models. So in unsupervised learning models, I don't really have a priori model in mind that I want to build. I just have a bunch of variables. I just have data, and I'm kind of shifting through this data and then trying to find something useful, right? And so in unsupervised learning models, we are basically trying to group the data. So if I have, for example, customer data, I can segment the customers into high-paying customers or low-paying customers or so on and so forth, right? And so these are typically what are called unsupervised models. Clustering, for example, is a very, very standard unsupervised model that people would build. K-means clustering, nearest neighbor clustering, self-organizing maps, singular value decomposition, or SVD. So these are all standard unsupervised learning models. And then there's another class of models called reinforcement learning models. And so basically in reinforcement learning, what happens is we take a small action and then we compute the effect of this particular action. If it is positive, we try to do more of it. If it is negative, we try not to repeat it, right? And so that's in a nutshell what reinforcement learning models are all about. So there's a famous reinforcement learning model that plays the Go game, and so it was able to beat the world's best player, right? And so there are lots of learning models that people have built, that can be used to try something different. If it helps to reach a particular goal, then you try and do more of it. If it has a negative consequence, then you don't repeat the same process. So that's typically what's called the reinforcement learning model. And some examples are, ANN, artificial neural networks, learning automata, Q-learning, MDP, Markov decision process modeling, and things like that, right? And so there are different classes of standard machine learning models that are available. So in machine learning model, if the onus is on the builder to come up with the appropriate data. So for example, I need to come up with what are my independent variables, what is my dependent variable, or in other words, what is my target or response variable, and what are the independent variables that have an impact on it. And then I'm trying to come up with the linear or a non-linear kind of relationship between the independent and the dependent variables. In deep learning, the emphasis is on having the model itself learn the features that have an impact on the dependent variable, right? And so in a lot of times, it's very hard to come up with the training data set. So in deep learning, the focus is on trying to get away from being able to provide, labeled data, because it's very time consuming and, it may be very complex. We may not even understand. So for example, if I have image processing kind of an application, I don't even know what features to input to the model, right? And so in deep learning, the focus is on trying to get away from this whole business of what is called feature engineering. Feature engineering basically means what are the important variables, independent variables that has an impact on the dependent variable. So that's what sort of the machine learning models do. In deep learning, we kind of try not to do this feature engineering process. Let the model itself figure out what's interesting and then use it to build the model. And so there are lots and lots of examples of deep learning applications. So one type of application is image analysis. So if you have lots of medical images, and then you can build deep learning models to kind of interpret the images. Like, for example, if you're looking for malignant cells, for example. So people have built very, very sophisticated deep learning models that can have an accuracy rate of 99.9%. even, they do better than, radiologists sometimes, right? And so one class of deep learning models are applicable for kind of doing image analysis. If you extend that a little bit further, video analysis, and so looking at frame by frame, and then trying to figure out, what you see in every frame, and then trying to come up with some sort of tags, or figuring out what action is being taken in a short video clip, for example. So if you think of autonomous driving, video analytics has to be done in near real time, because when the car is moving, it gets constant video input, and then it needs to decide what objects it's seeing. Is it seeing a fork in the road? Does it need to turn left or right? Or, all those kinds of decisions have to be made in near real time so that we can control the movement of the car, right? And so video analytics uses a lot of very, very sophisticated deep learning models. Text analytics, looking at lots and lots of medical text, for example, you would be able to identify important proteins or important compounds, or identify protein to protein interaction or protein to chemical interaction, right? And so there are lots of very good applications of text analytics, named entity recognition, and kinds of applications where you can use deep learning models. There are basically 3 or 4 types of deep learning models. I don't want to spend a lot of time on it. So basically, the very simple type of deep learning model is what's called a feed-forward network, deep forward nets. Basically, it's a neural network that kind of tries to emulate how a human brain functions, right? And so the basis for a deep learning models is basically a regular neural network, and so a neural network is nothing but you have lots of nodes or neurons connected to each other, and then there's input to the set of nodes, and then these nodes do some processing, and then eventually they generate an output. And so in deep learning architectures, so you can have a lot more of these hidden layers, and then you can control how many neurons there are in each of the layers, and so there's a very good mathematical foundation for these kinds of things, and so these actually scale up very well. And so every deep learning model is based off of a standard fully connected neural network. There is one type of neural network called CNN, or convolutional neural networks. So these are very good for processing images. And so the example that I gave before, looking at an image and then trying to identify malignant cells, for example, is built, using this CNN technology, right? And so we can provide lots and lots of images, both positive and negative images, and then from these images, the model would try to identify patterns that it can use to kind of identify malignant cells or regular cells. And so CNN applications are very well received within the healthcare domain. There's another class of models called recurrent neural networks, or RNN. So the CNN focuses on the spatial relationship between data elements. RNN focuses on temporal relationship, or the time aspect, the longitudinal aspect of the data. And so if you think of speech synthesis or text analytics, the current word has, relevance to what came before and what's going to come after it, right? And so we need to keep track of the spatial aspect or the time aspect. And so in these kinds of models, we kind of, try and keep track of the sequence information. So over a period of time, we can identify some temporal relationships between the data elements. And so that's very useful in speech recognition, text processing, and NLP kinds of applications. Here's a taxonomy of the different kinds of models that are available. And so, no, I'm sorry, this is a slide, busy slide, but these are all some standard models that are available. One of the things that we have to pay attention to is, okay, fine, we can build all of these different kinds of models, but then how do you know, these models work well? And so there are lots of metrics, that we can use. How robust the model is, how scalable the model is, can we interpret the results? And then we can also compute a lot of metrics like accuracy, misclassification rate, true positive, true negative, F1 score, and things like that, right? And so we can build all of these machine learning, deep learning models, and then compute all of these metrics, and then figure out which model is very effective for a given application. Okay, so that's sort of a quick summary of machine learning, deep learning, and AI, in terms of terminology. So now let's look at some applications of AI ML, particularly in the context of being able to deal with a pandemic. So we just went through a pandemic. So how could AI ML tools and technologies be used to kind of combat pandemics? So there are a number of areas in which we can apply AI ML models. The simplest one is identifying who's most at risk, doing some sort of risk analysis. We can use machine learning models for diagnostic purposes. AI deep learning models are used for, in the process of drug development, repurposing drugs, for example, starts with some AI deep learning kind of work. How disease would spread, we can try and do some predictive models there. We can use machine learning models to even better understand viruses, and try and map where viruses come from, and be even able to predict when the next pandemic might come, right? And so these are all different areas that people are working on, where AI and deep learning, machine learning models could be applied. So in terms of risk assessment, for example, you can do risk assessment at different levels, if you will. And so we could use machine learning models to study infection risk, predicting the risk of infection based on some demographic information, like, for example, age, pre-existing conditions, hygiene habits, social habits, and so on and so forth, right? And so we could build a very, very effective machine learning model using these demographic information. And so when we have a new patient or somebody comes in, if we input the values of the independent variables, then we would be able to kind of identify the risk level, how risky this person is in terms of being able to get infected, for example, right? So you could do some sort of analysis of risk of infection. You can also apply the same kinds of techniques to provide to kind of predict the severity of the risk as well, right? And so you can build models that can potentially predict the likelihood of a patient developing, let's say, ARDS, acute respiratory distress syndrome, right? And so we can not only kind of assess the initial risk, but also try and predict how severe somebody would be infected by a given virus. We can also build models to predict outcomes, outcome risks. If we give a particular kind of a treatment, what kind of outcome would we expect? And so based on historical data, we should be able to build treatment outcome models as well. So using machine learning models, we can come up with risk assessment, given a particular kind of a virus that we are interested in studying. Okay. Machine learning models are also used for patient screening, right? And so facial recognition, using facial scans to identify symptoms. So as you walk through the airport, for example, right? So we have lots of facial recognition models that people have built to identify people that might be infectious, right? And so we can use machine learning models to be able to do those kinds of diagnostic activities, right? And so there are lots of wearable technologies that people use these days, and so those the data collected from those devices can also be useful, can be analyzed using standard AI machine learning models as well. You can build chatbots. People may interact with the chatbot, and then based on the information that they provide, we can also kind of figure out is somebody is at the risk of catching or carrying the virus. So patient screening could be done using machine learning models. As I mentioned before, drug development also involves a lot of machine learning kinds of activities. So typically, we can build these machine learning models that can help us identify what chemicals would interact with what proteins, for example. And so that kind of gives us or limits the search space to start with, right? And so vaccine development, drug development uses a lot of deep learning models kind of work. So, a good example would be that when we were developing a vaccine for Ebola, and so, people built Bayesian machine learning models with the viral serotype entry assay and the Ebola virus replication assay, and then try and come up with a vaccine. So this actually helped in developing the vaccine quite in a short duration. Identifying effective existing drugs, right? And so, like I said, there are deep learning models that people have built that can kind of model how certain drugs and proteins interact with each other, right? And so neural networks, trained on large DTA databases to generate lists of particular drug candidates, right? And so there's so many drugs available, and so the search space is very huge. And so if we can build some machine learning models, that would help us to at least narrow down the search space so that you can start with something more reasonable, right? And so deep learning models are quite effective. Kind of looking at how disease spread, predicting the spread of infectious disease. You can do a lot of social network type analytics and then try and figure out how the disease might spread over a period of time, or in a certain region, for example, how the disease might spread. And so there are machine learning models that we can use to kind of do network analysis and then kind of pinpoint some hotbed areas of virus activity, right? And so machine learning, deep learning models play a role in that kind of an approach as well. And like I said before, understanding how the virus interacts with the host, protein, viral host protein interaction. So PPI models can be developed using deep learning models so that we can pinpoint what protein within the virus we need to attack or to either control it or kind of minimize its negative impacts as well, right? And so developing PPA models would go a long way in combating the virus that causes a lot of difficulty, right? And so there are models like SVM models, hidden Markov models, and then artificial neural networks. Based on large volume of data that we have developed, we can analyze and then build these models so that we can kind of pinpoint what protein that we want to attack given a particular virus. And so if we understand the proteins that are part of a particular virus, and if we know what chemicals have an interaction with the particular protein, then at least it kind of gives us a starting point. And then obviously we need to kind of go through the rest of the life cycle to develop drugs or vaccines or so on and so forth. right? And so a lot of machine learning, deep learning models are used quite effectively in developing or repurposing existing drugs. So I think looks like I'm running out of time. So I'm sort of going to get to the conclusion part. Basically, AI, machine learning model, has a big role to play in fighting pandemics in general. And we can also use AI ML techniques for medical diagnostic purposes and providing appropriate treatments so that we can improve the quality of healthcare. And so at least, the intersection of computing, data analytics, obviously domain experts from the medical field. So it's an interdisciplinary kind of an approach. And so developing good and effective, deep learning models would obviously help to kind of provide quality care, and then at the same time also minimize the cost of healthcare. So that's the other big area where AI and ML is also used, particularly in the US. Healthcare costs are pretty tremendous, and so people are working hard to minimize the readmission of patients and how to be more effective in managing the hospital in terms of the resources allocation and stuff like that. Anyway, so I will stop my presentation now, and if there are any questions, I'll be happy to answer them.
So thank you very much, sir, for your very informative presentation. And it is very interesting also. It is this topic is a little bit outside of our thing, but even though you make it very simple and then make it clear what is a real concept between the MI and programming, and also you have given, you have been well differentiated between AI and machine learning. So that is in your first slide. You are very clear in that one, actually, sir. So my question is that is there any kind of plug and play programming methodology so that it will help the clinicians or the science background people and the engineer to work together? Because we have a lot of problems, but the problems we don't know whether the solution is there or not. So we need a kind of like a plug and play, or developing a prototype from the initial prototype, so that we can make you more understandable to your side, so that you also will be very clear in making that the algorithm or programming.
Right. Exactly. That's a very good question. So, obviously, people that are not used to this kind of work, terminology, it might look kind of, rocket sciencey, or, but actually, we can build very sophisticated deep learning models from existing libraries. So there are lots of libraries that are out there, and people have built very sophisticated models and well-documented models. And so we can start off with standard deep learning models, using many of the platforms like TensorFlow or PyTorch, right? And so there are lots of tools available. And so you don't need to be a computer scientist or a statistician, but all of these packages are sort of, even though you don't need to know all the math behind it and all that stuff, but as long as you know how the models function, at a high level, then we should be able to use it, right? And so part of the trick is to make sure that the data that you feed these models are good quality data, right? And so that's where, your role comes into picture. So, when you provide data, most of the time, I don't know what they mean, right? So I talked about, features or independent variables and dependent variable, right? And so, I can have 500 columns of data, but then, maybe 10% or 20% of them actually have some impact on the target variable, right? And so that's where the domain expertise comes in. And so together, I think, we should be able to build very sophisticated deep learning models, because I don't have a lot of medical background, but then you bring that to the table, and then I come to the table with computing background, and then we can start with the very basic, deep learning model. And then how do we fine tune it based on the specific application so that you get, good level of prediction. All right. And so interdisciplinary approach is what would make.
Is there any interdisciplinary courses available between the AI and the medicine?
I mean, so in our own medical school, I think, yes, we do have some courses that get into analytics and AI, ML kind of thing. So I'm sure there must be, in our Beaumont Medical School, I think there are some courses because we do work with the doctors here on some projects and stuff, and so we do interact with them. I'm sure there must be some like that in India as well. But off the top of my head, I don't have that info, but we can definitely find it. Yeah.
And sir, you have shown some kind of a methodology to how to validate the data. So some kind of metrics you have been shown to us. So this is an exact metrics can be followed, or by doing these metrics, we can able to give the accuracy. That is one more question also, how to determine the accuracy or detection of our the framed algorithm.
Right. Yeah. So basically, when we build a machine learning model, what happens is, so typically we build a model, we divide the data into training data set and evaluation data set. And so we train the model, and then we have a test data set that, new data that we feed in, and then we see how accurately the model predicts. So we create what is called a confusion matrix, which is basically nothing but for every record, how did the model predict, right? And so we keep track of it, and then we kind of, figure out what are the true positives and the true negatives, and then we can take some ratios and things like that. So we basically build a confusion matrix, and then we can compute accuracy, recall, precision, misclassification rate, F1 score. And so all of these metrics are standard metrics that we can use to judge the performance of a particular model.
Okay. So is there any AI in 3D scanning, sir? Because one of the major tasks is that getting a model, creating a model for 3D printing or 4D printing. So is there any kind of AI involvement or role in 3D scanning? Because already you can carry on, sir.
Right. Yeah. So the people have built very good models for 2D, like, if you're looking at an image, then it's easier. And so kind of doing volumetric kind of a modeling, I think that's where, a lot of the research is also happening now. And so, yes, there are efforts in that direction, but, it's still work in progress. So, the simple answer is yes. Definitely, I think that's an area that we can look into as we work on some projects together. Yeah.
So what will be the future of AI in healthcare, sir, from your point of view?
I mean, obviously, it's, it has a definite role to play. And then also, there's also the other thing that we need to keep in mind is, for every good thing, there's the flip side of the story is also there, right? And so these models could be misused, and so there's ethics in AI, and also kind of misuse of these models, particularly in the healthcare, for example. Who's liable, right? And so if something bad happens, I can't just say, well, my deep learning model said this, and that's why I did this procedure, or whatever the case may be, right? And so the whole aspect of the liability issue and ethical issues, diversity issues, and so all of these things are also need to be taken into account. And so, but nevertheless, I think these models have proven to be quite effective in terms of predicting an outcome. But how they predict sometimes might be hard to explain. But all we care about is how good the prediction is, and so from that aspect, I think AI models would be here to stay. But I think how we use it and how we apply it, we have to be the stewards of, the right use of these models, because there's
Is there
always
any
a negative side to it.
is there any regulatory bodies are involved in controlling the activities of this one, sir?
Right. So in business communities, for example, there are rules and regulations. So similarly, even within the medical community, how do you assess the effectiveness of these tools and technologies, and what happens if something goes wrong? And so there are laws that are being passed to kind of make sure that these things don't get misused. And so or else there will be very, very negative consequences, as we can imagine, right?
And there is the one question from Dr. Saras, sir. So what is the role can the end user can play in improving the accuracy? I think
So there are different ways in which we can do. One thing is getting the quality of the data actually does matter, right? And so if we have dirty data, then the models probably cannot predict that well. So cleaning up the data, aggregating the data, and making sure that we have the best quality data. But then the models themselves can be tuned in terms of how long do you train, because some of these models take a long time to train, right? And so how long do you train? The flip side of that is sometimes you overtrain, so it learns too much information from the examples that you're providing. But then when you provide a test data set, they may not have the same noise as your input. And so the model prediction would be pretty bad. During the training phase, the accuracy might be very high, but then during prediction, your accuracy might be pretty low. And so how far apart you are, and then there are certain things that we can do to combat overtraining or undertraining and things like that. So, we can play around with the architecture of the model itself, and also the whole life cycle, how long do you train and things like that.
So thank you very much, sir, for your patient, and I think people are very much interested. This topic is really different from the regular one. Actually, I hope most of our the delegates will benefited from your talk, sir. So thank you.
Thank you. Thanks for the opportunity, and feel free to reach out to me. I'll be more than happy to answer any further questions. So this is my email address. I'm not sure if I'm still sharing. Sugumara@oakland.edu. So thanks, everyone.
Thank you.
Thank you. Thank you very much, sir. We would like to honor the speaker with a certificate and a memento. We would also like to honor our chairperson with a certificate and a memento. Thank you, sir, for enlightening us on machine learning, which has touched many facets of research. Thank you very much, sir. We thank the chairperson, Dr. Ravi Kumar. Thank you all. We'll move on to the next session.
Thank you, Arti.
Thank you.